All right, we've begun recording. Are there any questions about what we've discussed so far? If not, let's begin. So I just want to remind you what we discussed last time. So the goal of last lecture and this lecture and the next two lectures will be to understand how to compute some things in Czech cohomology, in Étale cohomology, which so far we've described only in terms of a very abstract with derived functor definition. And then last time I started explaining how to compute it in terms of Czech cohomology, but that description was not so computable either. So let me just remind you of the sort of important things we've learned about Czech cohomology. So like the definition and just a couple basic facts. So first of all, let me remind you that if we had a cover U of X and a sheaf F on the Étale site of X, we defined a Czech complex relative to U. And let me remind you what that was. So that was you evaluate F at U. And then there's two maps from U cross U over X to U. And if you take the difference of the pullbacks along those, you get a map to F of U cross U. And then there's a map to F of U cross U all over X, and so on. Okay, so this was the Czech complex relative to a specific cover. And then we defined the Czech complex of the Étale site of F to be the direct limit over all covers U of the Czech complex associated to that cover. Okay, and let me remind you here this U was a cover of X. Or if you'd like, you can take a covering family and the definition can be slightly modified in that setting. So if anyone has questions or would like to see an explicit definition there, I'm happy to write it down. So does anyone want to see the definition for a covering family, or are you happy to assume, I mean, if you have a covering family which is finite, you can just take the union of all the elements and then that gives you such a U and that works. Okay, great. So Amelia has given me the thumbs up, and if no one objects, I will move on. So the main theorem. So the general warning. So the general warning is that in general, Czech cohomology. We defined HI Czech to be the cohomology of this complex. So this is not in general isomorphic to derived functor cohomology. But the theorem, which I'm not going to prove in this class, and you can take a look in Milne's Étale cohomology book, section 3 for a proof if you'd like, is that that Czech cohomology is canonically isomorphic to derived functor cohomology under the following conditions. So if X is quasi-compact and satisfies the following, so this following kind of funny condition. So any finite subset of X is contained in an affine. Okay, and then the remark, and there was some discussion of this in the Discord, which is that this is true, for example, if X is quasi-projective. So the discussion in the Discord was like, okay, so actually how do you check this if X is quasi-projective? And in general, you can just slice by a hyperplane that misses your points, unless you're over a finite field, when maybe you don't have enough hyperplanes to do that. So if you didn't see the discussion in Discord, you should convince yourself that this is still true for quasi-projective varieties over a finite field. And if you are stuck, you can look at the discussion in the Discord and see see why that's the case, and it's a fun little trick. Okay, so maybe before moving on, I want to remark. So there is a version of Czech cohomology which works for arbitrary sets and which always computes derived functor cohomology. So there's a version of Czech cohomology where covers are replaced by objects called hypercovers. Which are a bit technical to define, so I won't define them. And this always does compute derived functor cohomology. All right. Are there any questions about that? So this was meant as a recollection of what happened at the end of last class. Okay, so now let's start with new stuff. I want to introduce an important technical tool, which is a kind of generalization of the Mayer-Vietoris long exact sequence, and we'll get some kind of Mayer-Vietoris long exact sequence from it. Which is a special sequence called the Czech-to-derived spectral sequence. So this is a sense in which Czech cohomology is always related to derived functor cohomology. Namely, there's a spectral sequence which goes from some kind of Czech cohomology to derived functor cohomology. All right, and we're going to, so this is maybe familiar if you've seen a similar thing for sheaves on topological spaces. There's a totally analogous story. So let's make this object. So it'll be the spectral sequence of a certain double complex. So how do you compute derived functor cohomology? You take an injective resolution of your sheaf, right? So you take a resolution like this, and we proved such a thing existed because we proved the category of abelian sheaves on the Étale site has enough injectives. So this here, this complex here is called an injective resolution of F. If this complex as a whole is exact, and each of these i's are injective. Okay, so each of these things are sheaves, and the Czech complex is a functor. So we can make a double complex out of this complex by applying the Czech complex functor. So given a cover u to x, we can get a sequence of complexes. So we start with the Czech complex of I0. Okay, and so on. So this is a double complex, right? Because each of these objects themselves is a complex. So I'm going to think of the horizontal direction is coming from the differentials in this complex, and then the vertical direction is coming from the differentials in the Czech complex. Are there any questions about that? All right, great. So to a double complex, one can associate two spectral sequences, and one of them, yeah. So let's compute what happens. So first let's take cohomology in the horizontal direction. So can anyone tell me what this gives us? So what lives in place PQ if we take cohomology, if we take the cohomology going in this direction?
Sorry, just to visualize, can you write out a few of the terms of the?
Oh, sure. Yeah. So let's draw it. So first we get C0, U over X, I0. So that's just I0 of U, right?
Is it going to be the Čech complex of the cohomologies?
Yeah, that's exactly right. But yeah, so let me write a little bit since Arvin requested it. So here we get I0 again. So this is I0 of U cross U, and then so on. And this goes to I1 of U, which is the first thing in the Čech complex of U. This goes to I1 of U cross U. Okay, and so on. Right, so computing the cohomology in the horizontal direction, so the E2 page of the spectral sequence, we get the Čech cohomology, right? So these vertical complexes. Yeah, so what are we doing? We're taking global sections of this injective resolution and then taking their cohomology, right? So that's also known as derived functor cohomology on U to the n, right? So in other words, the vertical complexes after doing that will compute the Čech cohomology on U cross, on U of the following pre-sheaf, Hj of our sheaf F. So here, this is the pre-sheaf which associates to V just the Étale cohomology, the derived functor cohomology of F on V. Okay, so I did this a little quickly, and I'm intentionally doing that because this is the same story that happens for topological spaces. So you should convince yourself that there's a special sequence associated with this double complex, so this is the E2 page. So what do we do to get this? We take the horizontal cohomology in the horizontal direction, and then the vertical direction. So if we just take the cohomology in the horizontal direction, we'll get a complex computing this thing, and then when we take the vertical direction, we get this whole thing. All right, let's do it in the other order. All right, so what happens if we take the cohomology in the vertical direction first? So what is the cohomology of these vertical complexes? So my hint is that Čech cohomology, we proved last time that Čech cohomology of an injective complex is 0. Or well, in degree bigger than 0. So the vertical directions, these things just are the Čech complexes of these injective sheaves, right? So can anyone tell me what the cohomology of this vertical complex is?
0, because
so it's 0 away from the bottom row, right? So what is it in the bottom row?
global sections. Yeah,
exactly. So it's on the E2 page is just the global sections of well, so we first take it's this. So it's the cohomology of the global sections of xi. So this inner thing is what we get when we take the cohomology in the vertical direction, and then when we take the cohomology in the horizontal direction, we're just taking cohomology. So this is derived functor cohomology. Okay, so this special sequence is degenerate because we just get entries in one row. So this is also equal to the infinity page. Okay, so what that tells us, well, both of these things have the same E infinity pages. So that tells us we get a special sequence. So in particular, the special sequence of this double complex when you take cohomology in the horizontal direction and then the vertical direction. So I don't remember whether that's 2, 1 or 1, 2. There's some convention on this, which you can look up on Wikipedia if you so desire, which goes from the Czech cohomology on this cover U with coefficients in this pre-sheaf. So this cohomology pre-sheaf, and it converges to the derived functor cohomology. Great. Cool. Are there any questions about that? So an exercise. So an exercise here. So last time I claimed that if the functor, the Czech functor, which associates to a sheaf the sort of Czech complex of the Étale site, is exact on the category of sheaves of abelian groups of X on X Étale, then Czech cohomology is the same as derived functor cohomology. Okay, so the exercise is to prove this. So last time I claimed it follows from the theory of effaceable functors, and it does. So that's one way to prove it. You can unwind what Grothendieck does in Tohoku to check that that's the case, or look in Hartshorn book 2. But you can also prove it using this spectral sequence. So maybe the exercise is to prove this using the Čech-to-derived functor special sequence. Okay, and you'll see it's actually not so hard. You'll see that in fact this E2 page becomes very, very simple if C bullet is exact. All right. Are there any questions about that? So this is an exercise you should really try. It's like a good way to become friends with the spectral sequence. Cool.
Sorry,
Right.
this is sorry. Can I ask a question about the spectral sequence?
Yeah, of course.
So this U cover is just an arbitrary cover of X.
That's right.
So so given an arbitrary cover U, and you can get the spectral sequence of these degeneracies. I mean, you don't have to take the inverse limit of the cover.
I'm sorry?
You don't have to take the inverse limit of the cover of X.
That's correct, but take a look. So look at this. So this is something. This is the pre-sheaf that associates to a cover of U or a cover of X. Yeah. The cohomology, the derived functor cohomology of that cover. So it's not. It's computing the Étale cohomology, but it's computing it still in terms of derived functor cohomology. Right. Right. So somehow the point is that when you take the direct limit, well, if this functor is exact, so in this, for example, in the quasi-projective case, these things sort of disappear except in degree 0. So that's what this exercise is more or less about. But all right, start with some given cover. This can be very interesting, and we'll see in a second that actually, like the Mayer-Vietoris long Z sequence from cohomology is a special case of the existence of this spectral sequence.
Okay, thanks.
Yeah, so there's a lot of content here. So in particular, one thing this is saying, one thing we'll see in a second, or at least maybe we'll see in some sense in a second, is that the differentials in the Mayer-Vietoris long Z sequence are also differentials in this spectral sequence. So it's really, in general, a very non-trivial spectral sequence. And in fact, that's the case in topology too. So if you feel like it, you can develop, you know, a check to singular cohomology spectral sequence. So there's a notion of Czech cohomology for topological space, and it does in general, or for nice enough topological spaces, say manifolds, compute singular cohomology if you plug in Z coefficients. And the Mayer-Vietoris long-list sequence in singular cohomology is a special case, or can be pulled out of this spectral sequence. Yeah, great. Are there any questions about this? Okay, so now let's talk about Mayer-Vietoris. So Mayer-Vietoris is not about general covers. It's something about Zariski open covers. So here's the proposition. So suppose U, here is the union of some U0 and U1, where here UI subset U is a Zariski open. Okay, then the proposition is that there's a Mayer-Vietoris long-list sequence. So there's a functorial. Okay, and the proposition is more than there exists. It's that it's given in a particular way, but I'll construct it in the proof. There exists a functorial long-list sequence. And it's exactly what you would expect from topology. So it goes HS of let me write it out this way. UF to, so HS of, sorry about that, of U0 F direct sum HS of U1 F, and this maps to HS of the intersection. Okay, and then the next term is H of S plus 1, U F. Okay, and then you keep going. Okay, so this is exactly like the situation in topology. Okay, so what are these? What are these maps? So these are the restriction maps. This is the restriction map, and this is going to be a differential in the Czech-to-derived functor spectral sequence. Are there any questions about the statement? Okay, so what is this saying? This is saying that if you can compute on a cover and you understand these differentials, then you can compute on what is being covered. So for example, you know, you could take U to be P1, you could take U0 and U1 to be the standard affines, the standard copies of A1 inside of P1. Their intersection is a copy of A1 minus the origin. So this is saying that if you can compute on those affines, so A1 and A1 minus the origin, then you can compute on P1. Okay. I mean, hopefully this is a little bit familiar. So the proof, I'll just sketch, because it's actually a little bit more complicated than you might think. So the proof is to apply the Czech-to-derived spectral sequence to the cover U0 union U1 to U. All right, so there's actually some subtlety here. So let's actually see what happens, and I'm not going to give you the details. So what does the Czech-to-derived spectral sequence tell us to do? So it tells us to take F of U0 union U1. This maps to F of maybe, sorry, this should be a disjoint union, not a union. The actual union would be U. So let me make these disjoint unions. So then the next term would be this thing. So the double intersection of this thing over U. Okay, and then the next term would be the triple intersection and so on. Okay, and so on and so forth. Okay, and note that none of these objects are actually empty. Right, like if you take the fiber product of U0 disjoint union U1 over U, you're always getting copies of U0 and U1 in their intersection inside of that fiber product. So this is like not what you typically think of when you take the Čech complex of an open cover, right? Like often people think about in terms of like the alternating Čech complex where you don't get all this extra junk. Okay, and so the claim is that this complex is quasi-isomorphic to the following, to f of U0 disjoint union U1 mapping to the intersection. So this two-term complex. Okay, and then what is this? This is the same as f of U0 times f of U1. Just because U0 and U1 together form a covering family of U0 disjoint union U1. All right, so this is a claim that you should prove in an exercise. Okay, and once you have this, so given this, so the Čech-to-derived spectral sequence is now just it vanishes, so that the E2 page vanishes except for the first two columns. So let me draw a picture. So here, here's two columns and here's some rows. Okay, and then what happens? So suppose you want to compute H1, right? So you're looking at these two rows. So what happens? So there's now some differentials which go like between here, for example, and here, and so on and so forth. Okay, and if you just write down what it means that you're computing the spectral sequence, these differentials will be exactly the differentials in this Mayer-Vietoris spectral sequence. So you'll exactly see, well, what is, like, let's just look at HS here. So HS is going to be something built out of this diagonal of slope 1. It'll, let's see, it'll, oh, I think I drew the differentials going the wrong way. So they actually go this way. So it'll map here, it'll hit the kernel of this differential. Okay, and then the image of this differential, this object, will be a subset of H2 and then so on and so forth. So that will be this H2 will have a image from the quotient here, it'll map into here, and then again there will be another differential and so on. So this is a general phenomenon that if you have an E2 spectral sequence which only has two non-vanishing columns, that data is exactly the same as along the exact sequence. Okay, so the claim is that this data is the same as along the exact sequence. Okay, and you should write it out and check that. Are there any questions about that?
Is that little sort of claim the reason why we're using Zariski opens rather than just like?
Yeah, so this claim, that's right. So this claim is not false, is not true for general covers, right? So for example, if you took a you know, the map GM goes to GM via squaring, right? It wouldn't even make sense. Like the double intersection will be well, it won't be connected, but it would be like there wouldn't be a distinguished component of it. Does that make sense? Yeah, so this claim here that's worth remarking. So this claim uses that this is a Zariski cover. So if you took a general Étale cover, there would be there would be no reason for this to be quasi-isomorphic to a complex of finite length. Does that clear things up? Okay. So with this, we can actually now compute the cohomology of our first sheaves. So here's a theorem. So suppose X is a scheme. So this theorem is true actually for arbitrary schemes, but I'm only going to prove it in a special case. So suppose X is a scheme and F is a quasi-coherent sheaf on X. So for example, OX. Then here's two things you can do. You can take HI of X with coefficients in F. So this is the usual like Zariski cohomology of a quasi-coherent sheaf. The claim is that this is canonically isomorphic to the Étale cohomology of the associated quasi-coherent sheaf on the Étale site. So remember that was just obtained by, for any Étale morphism to X, just pulling back F to that Étale morphism. This is the same, if you'd like. You can also do this on the FPPF site. And remember, we also said the category of quasi-coherent sheaves on the FPPF site is the same as the category, is canonically equivalent to the category of quasi-coherent sheaves on the Zariski site of X, or the usual scheme X. All right, so this tells us how to compute the cohomology, the Étale cohomology of all quasi-coherent sheaves. Are there any questions about this statement?
The first one was the Zariski thing?
Yeah, so this is just the usual cohomology of a quasi-coherent sheaf.
Okay.
Which, if you'd like, you can think of as the cohomology, the derived functor cohomology on the Zariski site. Maybe it's worth mentioning, actually. So before I prove this theorem, so a remark is there's already a version of this which is non-trivial, right? So which you've probably already seen in Hartshorn. So you can look at the derived functor cohomology. So if you'd like, you can think of that as the cohomology relative to the category of sheaves on the Zariski site of X, of F, right? So here, when I say sheaf cohomology, that's not something, like you can view that in terms of sheaves on a topological space, but really this is the same as for example, this is something that really only depends on the category of sheaves. So you can view this as X die in the category of sheaves on X Zariski of the constant sheaf Z against F. Can anyone tell me why these two things are the same? Maybe I'll write it this way. So I'm writing it this way to show you that it only depends on the category of sheaves and not on the topological space. So can anyone tell? Yeah, so Benjamin gives the right answer. So we're taking the the derived functor of global sections, but global sections are just the same as Hom from Z, and X is the derived functor of Hom from X of Z dash is the derived functor of Hom from Z. Okay, cool. Okay, and well, this thing is the same, I claim, as HI in the category of quasi-coherent sheaves of X, coefficients in F, if F is quasi-coherent, where this is, for example, defined as X die in the category of QCO of, let's say, OX F. Okay, and again, that's the same reason, and it's maps from OX into a quasi-coherent sheaf are the same as global sections, or that's the true for any sheaf of OX modules. But nonetheless, I claim this canonical isomorphism is not formal. And the reason why is that we're taking X in different categories. Like we're taking X of the same kind of functor, like global sections, or derived functors of the same kind of functor, global sections. But what it means to be a derived functor is relevant to an ambient category. And here, if you take the category of quasi-coherent sheaves, that's much smaller than the category of all abelian sheaves, right? So this isomorphism is really not formal. So does anyone know why it's true actually? And maybe I should actually assume X is QC/QS or something. But I think this is true in general, but I maybe don't know how to prove it. Yeah, so Benjamin gives the right answer. So the reason is that if you take an injective quasi-coherent sheaf, that's Flask. So it also computes derived functor cohomology. Like it's Flask as an abstract sheaf. So it also computes derived functor cohomology. That's right. So I would like you to think of this theorem as a beefed up version of this one. So it's saying that if we compute, so we already showed that the category of quasi-coherent sheaves on the Étale site is isomorphic to the category of quasi-coherent sheaves on the Zariski site. So if we were just working in QCO, we'd already have an isomorphism to this thing. But here we're saying, oh, we're working in this much bigger category of sheaves on the Étale site. And we're saying we still have this isomorphism. And this argument that we say injective quasi-coherent sheaves are Flask, as far as I know, I don't know how to make that argument work to prove this theorem. So we needed a new argument. All right. Are there any questions about what we're proving here and this analogous statement for the Zariski site? All right, let's take maybe a 2-minute break since we've been going for a while, and then I'll come back and prove this in a pretty general special case. Oh, there was some noise. So does anyone have any questions during the break or anything they want to chat about? Oh, so Benjamin asks in, so if you've been injective on Étale, is it true that its restriction to the Zariski site is injective? I believe that is true, yes. I would have to, let me think about it just to check. Yeah, I think that's true. Yeah, the issue is that it's, so I think that if you, the issue with trying to imitate this proof is, okay, so you pick an injective quasi-coherent sheaf, that gives you a quasi-coherent sheaf on the Étale site. I see no reason for it to be acyclic. I mean, I think after the fact it is acyclic, but I don't, yeah, it's not clear to me what, like, I don't think it's Flask in any sense anymore. I mean, it's possible there's some argument along those lines, but I don't know it if so. Are there other questions?
Excuse me, so what exactly is the difference between these two things you wrote down? Is it that on the right you take only quasi-coherent injective resolutions?
Yeah, that's right. So here you're allowed to compute this by taking injective resolution by quasi-coherent sheaves. But the issue is that being injective in the category of quasi-coherent sheaves is not the same thing as being injective in the category of sheaves. It's much harder to be injective in the category of sheaves because you have to satisfy a lifting property with respect to more maps.
So can you maybe sketch, if it isn't too hard, how to come up with a quasi-coherent injective sheaf? Because I haven't seen this.
It's not so easy. I mean, yeah, it's, and as far as I know, maybe, let me think for a second. Yeah, like I maybe don't know how to do it without having some quasi-separatedness or something like that. But what I would say is, like, even if you don't have enough injectives, like a posteriori, like derived functor cohomology doesn't require the existence of injectives, right? Like the definition of a derived functor is a unique. There's a unique such thing if it exists, and you can prove it exists, for example, by the theory of the calculus of fractions, for example. So Benjamin asks about what I mean by FPPF here. So here I mean the small site. I think it's true for the big site too, but let me just be careful. And if you say the big site, yes, there are more quasi-coherent sheaves on the big site. On the small FPPF site, they're all the same. Jose asks, is the theorem also true for other sites? Yes, for some other sites. So for example, for the Nunavut site, it's true. I mean, it's true for any site which is coarser than the FPPF site and finer than the Zariski site, I think. Are there other questions? So the small FPPF sites means that the objects are flat and finitely presented X schemes. That's right. And then covers are covers. Yeah. Great. Are there other questions before we start again? All right, let's start again then. So I'm actually gonna prove the theorem in a fairly special case. So I'm gonna prove, so if X is quasi-compact and separated, and the big assumption I'm gonna make is that Czech cohomology computes derived functor cohomology. Okay, so this statement is true in general, but I'm only going to prove it in the special case. And we know from this result that I quoted from Milne that this latter assumption that Czech cohomology computes derived functor cohomology is not so strict. Like it's true for quasi-projective schemes, for example, but this theorem is true without it. Okay, so let's prove it. So first of all, I claim every cover can be refined to a finite cover by affines. Okay, and this already uses quasi-compactness. So this is not so hard. So take a cover and then break up the pieces showing up in the cover into affines, and then you get a finite cover by quasi-compactness. Okay, so now let's consider the following situation. So let's suppose X is affine now. And U to X is an FPPF affine cover. So in particular, U itself is also affine. So then the claim is that the Czech complex for U over X with the coefficient in any quasi-coherent F is actually exact. So let's suppose we're on an affine, so we can assume F is the quasi-coherent sheaf associated to some module M. Okay, so let's check this claim. So can anyone help me rewrite this this Czech complex in terms of rings and modules? So everything inside is an affine, and we have a module, so we should be able to rewrite everything, right? So let me choose some notation. So suppose U is spec B, X is spec A. And then, well, F is a quasi-coherent sheaf on F on X. So here M should be an A module.
Is this going to be the
Go on.
same thing that we had in our descent stuff?
That's exactly right. So the complex you get is, well, here, and let me just write it. Here's M pulled back to U. There are the sections of M on U. Then this maps to M on U times U, and this maps to M tensor B to the cubed. Here, all these tensors are over A, and then so on. Okay, and this, we had a name for it. We only really studied the first two terms of it, but I think I made a remark. This is called the Amister complex. Okay, and what we did is we showed it was exact, or we showed that if we put an M here, so maybe let me actually put the M here. So this is, so we showed that, this part of it, that M is exactly the kernel of this map. Right, and let me remind you what the idea was. We argued that since B was a FPPF A algebra, so faithfully flat and finally presented A algebra, we could check this after tensoring with B, and then we had a section, and the section let us write down some section to these maps. So in other words, a null homotopy. So the claim is that this is exact, this complex is exact, by exactly the same argument, as in the proof of descent. And I won't give you the details, but I'll write down the hint. So base change to B, and then write down a null homotopy. Using the section. Okay, so what does the claim imply? So can anyone tell me what this tells us about Czech cohomology? So what does this tell us about the Czech cohomology of U over X with coefficients in a quasi-coherent sheaf? So Benjamin says it vanishes. So it vanishes away from degree 0. So it's 0 if I is bigger than 0. What is it in degree 0?
Global sections.
Yeah, so it is what Czech cohomology always is. It's global sections. So, and then this is again for F quasi-coherent and U X affine. Okay, so now so 3. Now I claim that the Czech cohomology of let's say the Étale site F is the same as the Czech cohomology of the FPPF site of F. Well, I haven't said what Czech cohomology is, so let me just say on the Étale site. You can make sense of Czech cohomology for the FPPF site too, but I didn't prove enough about it. So let's do it for the Étale site. So the claim is that this is again f of x for star equals 0 and 0 for star bigger than 0 if x is affine and f is quasi-coherent. So here. So can anyone explain to me how to deduce this from the previous statement? So we showed this not for arbitrary covers, but we showed this for Étale covers, for affine covers, sorry, right? So how do we get the general statement? So remember, this is the direct limit over all covers, but I told you in step 1 that every cover can be refined to an affine cover. Right, so the proof is that affine covers are cofinal in the set of covers, in the diagram of covers. Cool. Okay, so basically what we have, we're taking it. That's right, Sophia. Yeah. Yeah. So we're taking an inverse limit, but every time or a direct limit, but every time we have something zero, we can just kill it by something non-zero in the Czech cohomology of some cover. We can just kill it by refining to an affine cover. That's another way of saying that. Okay, so now let's prove it for x. I guess let's suppose it's separated, and suppose Czech cohomology computes derived functor cohomology. And x is quasi-compact. So this is where I'll stop the proof. So can anyone tell me how to complete this step?
Using the spectral sequence on like an affine cover.
Exactly right. So take an affine cover. U to x, just like a cover by a Zariski cover, for example, and use the Čech-to-derived spectral sequence. Okay, so can anyone tell me, just to make sure you're following, so how did we use separated here? Yeah, exactly. So when you write down that special sequence, you'll get things like the derived functor cohomology on the quintuple intersections of the affines that showed up in your cover. And we need to know that cohomology is zero, which it should be, which it will be by the previous result if those intersections are affine. Okay, so you should check this last step yourself. You can push this argument a little bit more. I'm being a little bit lazy here, but I don't think we'll ever have to worry about a scheme which doesn't satisfy these properties in this course. All right, so now we can compute some examples of Étale cohomology. So let me just start. So suppose X is projective space, and F is OX, for example. So can anyone tell me what is the Étale cohomology of Pn with coefficients in the Étale sheaf associated to OX? So Pn is a quasi-compact separated scheme, and it certainly satisfies this condition on finite sets being contained in affines. So so we can compute Czech cohomology via derived functor cohomology via Czech cohomology. So the previous theorem applies. So what does it tell us?
It's just going to be the standard cohomology of projective space, right?
Exactly right. So for affine space, this is the ground field, or the ground ring, if you'd like, if I equals 0, and 0 if I is bigger than 0. Great, we did an example. Amazing. All right, so let's do a more fun example. So suppose X is a scheme in characteristic P. So it's a scheme in characteristic P. Maybe let me make it a scheme over FP. Over FP is, and let's just assume it's quasi-projective, so we can apply the previous theorem for ID. So I want to write down the Étale cohomology of the constant sheaf FP. So this is something that people sort of rarely do, and we'll see why in a second. We'll see it's not so well behaved necessarily, but I claim this is something we can now compute given what we've done. So can anyone tell me how they might get at this? And my hint is that maybe, I mean, so how do you compute the cohomology of a sheaf? You like try to put it in a short exact sequence with sheaves you know, and then like you compute the cohomology, then you get a long exact sequence in cohomology, and then you try to compute you try to compute using that long exact sequence. Okay, so the only sheaves we know how to compute the cohomology now are quasi-coherent sheaves. So if we want to compute the cohomology of the constant sheaf FP, we want to try to put it in a short exact sequence with some quasi-coherent sheaves. So does anyone know how to do this?
Can we do some kind of Frobenius?
Yeah, you can do some kind of Frobenius. Yeah, so if you look at the map, so let's look at the map from GA. So GA here, this is just A1, right? And this is the, if you, it's like maps into A1. If you'd like to A1. Sorry, I just spilled a bit of coffee on my iPad and now I can't write on it. And in other words, this is, so GA of some U, oh my God, is just OU of U, right? Sorry about that. Hopefully this will dry up soon. Okay, so FP is the fixed points of Frobenius on GA, right? So we can write down a short as a sequence of sheaves, or even of schemes, FP to GA. Well, let's not worry about right exactness yet. So what is this? How do we write down a map whose kernel is the fixed points of Frobenius? So Frobenius is like taking p powers. So fixed points of Frobenius are what? What cuts out the fixed points of Frobenius?
Identity minus Frobenius.
Yeah, or Frobenius. Yeah, either way. So this we can write as x to the p minus x. So if you'd like, this is the map from the sheaf O to O, which sends a function f to the p minus f. But you can also think of it in terms of the object representing the sheaf GA, namely the affine line, is like the map x to the p minus, like x goes to x to the p minus x. Right? So is it clear what I mean by this? So the claim here is that this sequence is exact. Okay, and what's the proof? Can anyone tell me? So this is a sequence of sheaves, but I claim one can see this using the Yoneda lemma. Yeah, it's kind of like the exponential exact sequence. So this is called the Artin-Schreier exact sequence is the name for this. So the proof is just that this is true at the level of, well, you can say it's true at the level of representing objects, depending on how you think about things. Or you can just check it directly. Like, what do you need to check? You need to check that if you have a function here, a function on U, which is an Étale X scheme, which is which is killed by x to the p minus x, then it came from the ground field FP. And that's something you can just check by hand.
So isn't the GA to GA surjective?
That's going to be the next claim. Yeah, so where f to the p minus f equals 0 implies f is constant. Okay, so that's left exactness. So now I claim, in fact, this is short exact. So in fact, I claim that this is exact. So the only thing that's left to check is that this is a surjective, a map of sheaves. So that this is, so we prove, so what do we need? We need that GA to GA, sending x to the p minus x, is an epimorphism. So can anyone prove this for me?
I mean, we just need to be able to solve x to the p minus x minus some.
Yeah, so we need to, so we need, e.g., so given, you know, some function f in OU of U, which is the same as GA of U, we need to write, we need to solve, as you say, x to the p minus x equals f, Étale locally. On U. Okay, so here's how you do that. So we have this map U to GA, that's F. So there's a kind of natural place for this has a solution, namely due to space change. Okay, and then the claim is that this is an Étale cover. So why is there a solution? Well, I mean, I need to write down a function on this cover which satisfies it, and well, it's this one. So can anyone tell me why this is an Étale cover?
Because it's the base change of an Étale cover.
Yeah, exactly. So x to the p minus x is an Étale cover. And the key ingredient there is the observation that x to the p minus x is Étale. And why is that?
The derivative is -1.
That's exactly right. Yeah, the derivative is invertible. It's -1. Perfect. Okay, so what this tells us, so the corollary, and this is the answer to our computation, is that there's a long exact sequence, well, associated to this short exact sequence of sheaves. So what does it look like? So we get 0 to h0 x Étale fp to h0 x Étale ga. That's just h0 xox, right? So this is h0 xox. And that's like the usual thing we know how to compute, right? This is of what we just proved. So this goes to h0 xox, the same thing. That goes to h1 x Étale fp, goes to h1 xox. That's again something we now know how to compute. Goes to h1 xox. And that goes to h2 xfp. Okay, and so on. And all these maps are also understandable. They're just the maps given by x to the p minus x. So just as an explicit example, and then I think we're out of time, if x is a1, so that's spec of fp adjoint t, we get an exact sequence 0 to h0 a1 fp. That goes to h0 ox, which is just fp adjoint t. That goes to fp adjoint t again, via the map t goes to t to the p minus t. And that goes to h1 of a1 fp. And what's next? So what's next is h1 of a1 with coefficients in ox, which is what?
0.
0, exactly right. It's the cohomology of a quasi-coherent sheaf on an affine. So what that tells us is that, okay, h0 is the kernel of this map. That's just fp. h1 is the co-kernel. Okay, and the co-kernel is actually huge. So this is huge. So, okay, so this is why I say that Étale homology with fp coefficients is not well behaved. If you took a projective variety here, well, these things would be finite dimensional, so you get better behaved things, but it still would not have the expected dimensions. And we'll discuss this next time. But we're out of time. So let me stop recording. And thank you all so much for coming. I'll stick around a little bit if any of you have questions. So, anyone have questions? Thank you to everyone saying thank you.